I've got a manufacturing company, and we're counting the number of defects. And so the number of defects in an hour is a Poisson of 2.5. X equals defects. Can't see that, can you? X equals defects in 1 hour. And part B is the quote again. So it is that the defects are independent, and also that the mean rate is constant. Sometimes that might not be true in a manufacturing process. They might make more mistakes at the beginning of the day when you first turn it on, or maybe as if it's been working for a long time. So that assumption that the mean rate is consistent all the way through. So question part C. Part C then, 2 faults in 1 hour. So that's the probability that X is equal to do. Should we use the formula for that one? And it's e to the minus lambda, lambda to the x over x factorial. Let's just tap that into the calculator, and that gives us 0.2565. So I'll round that to 0.257 to 3 figures. Part D. Find the probability in a 3-hour period. So let's go y equals defects in 3 hours. And that means y is a Poisson. The mean in 3 hours is 7.5, isn't it? 3 times that. And we want the probability of at least 6. So greater than or equal to 6. And we'll just grab the calculator to do that one. So I'm doing the Poisson, I'm doing a greater than or equal to 6 with a mean of 7.5. That's what I'm doing, isn't it? That's giving me 0.759, 3 figures. And part E, we've got to change it again, haven't we? This time we've got a 4-hour period. So Z equals defects in 4 hours. And I know you're getting annoyed of having to write this out every time, but I think it's worth it. And the mean in 4 hours, of course, is 10 for those. And we want the chance of there being at least 7. At least 7. So greater than or equal to 7. I could probably just go back and change this, can't I? So just go back one level. Mean's now 10. X is now 7. And that's giving me 0.8698. So I'll round that to 0.870.